couple states below.
So this is the concept video for functions of several variables. So in single variable calculus we had functions of one variable, and usually that variable was x. And the way these worked was you put in some number for x, let's say x equals 1, and you got out some number, let's say 3. So we would often show this graphically by setting y equal to f of x, and we would have the x and y axis. We would have some curve as f of x, where x was the position along any along the x-axis. So let's say we have x1, and f of x was the height of the curve above the x-axis. So this would be f of x1. So another way of looking at that would be these functions turn some domain or some interval and you map them onto the set of real numbers. So for example, if our function was square root of x on 0 to 4, we take all these x values and we assign a number to these x values. So let's, for example, we have like 0, 2, 3, 3.5. So the function would assign a value to these numbers, a real number. So now we could interpret these as, like, let's say f was our temperature and x was position. So f of x just tells us what our temperature is depending on where we are. So if we're at like x equals 3, then our temperature would be, let's say, 60 degrees Celsius. So now we have multivariable functions. Sorry about that. And these will have, so x here was called the argument of the function, and that just means what you're plugging in. So here we have two arguments, x and y, and we'll be setting these equal to some z. So if we have a three-dimensional space with a y-axis, x-axis, and z-axis, so this y and x, there's just the regular y and x-axis we're used to, but rotated and on the ground. So we're kind of looking down. These are our eyes. We're kind of looking down on the x and y axis, as if we're looking at the graph on a piece of paper. So for these we get, so up here we got some curve, and before I go into that, so now if we have a point, let's say 1, 3, we can plug that in as f of 1, 3, and we'll get some value such as 5. So once you combine all these points, we get a surface. So let's say we went to 1 and 3 on the y-axis. So this is the point 1, 3. And it corresponds to some height of 5. So every point on the surface, every point in x and y has a associated value with it, and each of those values is what's on the surface. So z is just the height of the surface at any point xy. And what these do is they take some domain. So if we had some domain here called d, so it's not just an interval anymore because we have more than one dimension, and we put this onto the set of real numbers. So any real numbered height. So we could also have the surface doesn't need to be above the xy axis, it could be above and below. And I'll just erase all these. So the surface could cut through the xy plane. So we can look at the domain of these functions. So sometimes you'll have a restricted domain, so and you'll be told that x is greater than 0 and y is between 1 and 2, for example. So the domain here is just this. But some functions will have domains, a restricted domain, and you don't need to be provided this information. So what you need to watch out for is square roots, logarithms, and denominators. So these, what's under the square root must be greater than 0, so it must be positive. Argument of these must be greater than 0, and these they can't equal 0. So let's do an example.
And roll me to the door. I'm going where my body leads me. I can fend for myself with what looks I have.
You have f of xy equals square root of y squared minus x. So this quantity under here, y squared minus x, must be greater than 0. So if we solve this inequality, we'll get x is greater than y squared. And if we graph this, x equals y. It's a parabola opening to the right, and x must be greater than, or sorry, this should be less than, sorry, because we're subtracting this over. So x must be less than y, so, or y squared. This is y squared, and we want our x values to be less than that. So the domain, this is everything to the left of this parabola. And then we also have range. So that's just the different z values, or values that f of xy can take. So if we had f of xy equals 1 minus x squared minus y squared, and we can look at this as 1 minus parentheses x squared plus y squared. So we know that what's under here must be greater than 0, because it's a square root. So that means that x squared plus y squared must be less than 1. So if we know that this quantity here must be less than 1, or less than or equal to 1, because this actually can't equal 0. So I should have added that here too, equal to. So that means the maximum value this can be is 1. So let's check it out when x squared plus y squared equals 1, we have 1 minus 1, which is 0. So this is going to be the smallest value that f is going to take, because this gets smaller as x squared plus y squared gets bigger, and the maximum x squared plus y squared can be is 1. So now we look at the other side of this. What's the smallest x squared plus y squared can be? And that's x squared plus y squared equals 0. This can't be negative because x and y squared are both positive numbers, or 0. So at x squared plus y squared equals 0, or f of x y equals 1 minus 0 square root, which is just 1. Square root of 1 is 1. So the range is 0 to 1. Or you can write it as in this bracket notation. So the last thing we're going to talk about with these is level curves. So these surfaces are hard to visualize. So we're going to put them in terms of things we know we can easily visualize. So for example, we had f of well, level curves are just when you set this function equal to some value c. And then now we just have these two variables, and we can solve for x in terms, or y in terms of x, or other known graphs, like a circle. We have x squared plus y squared equals some radius squared. So basically we can find what this surface looks like at different heights. So I'll just do an example. We'll use that function that we were talking about before, f of xy equals square root of 1 minus x squared minus y squared. And we can set that equal to some c. And if we square both sides, we get c squared equals 1 minus x squared minus y squared. If we solve for x squared plus y squared, we get x squared plus y squared equals 1 minus c squared. And we can see that this is a circle, and the radius of the circle is square root of that, square root of 1 minus c squared. So now we can graph these do it right here. So let's say that for c equals 1, then x squared plus y squared is going to equal 0. So we're going to have a circle of radius 0. And let's say c equals 0, then we have x squared plus y squared equals 1 minus 0 squared, which is just 1. So we have a circle of radius 1. And everything in between, let's say c is 1/2. We have x squared plus y squared equal to 1 minus 1/4, which is going to be 3/4. So our radius is square root of 3/4, which is root 3 over 2. So let's just say that's right here. So now you can see we have different level curves corresponding to different levels of c, and c is just the height of this surface. So if we want, we can look at this in the xyz plane. So we know when the height is 0, we have this circle, and we know when the height is 1, we just have this point, and when the height is 1/2, we have another circle, and that didn't turn out that well. So if we keep graphing these, we'll see that we get a sphere, half a sphere. So that's what these level curves tell us. If we keep getting more of these values for different c's between 1 and 0, we'll get concentric circles, and once you stack those up, you get a sphere. So that's all I want to say about functions of several variables.
Before the devil made me